All right, welcome back. We are here to talk about differentiation rules for calculus. And we've been talking about the derivative a little bit lately, and we had a definition for the derivative, which you should know. I'd like you to know the formula for the definition of the derivative, but I'd also like you to just understand what the derivative represents. It can calculate the slope of the tangent line. But what does that mean? It is basically a measure of how steep the curve is at that point of interest. So anyway, we understand conceptually what the derivative is, and we also have a formula that can help us calculate the derivative. What we're going to be doing in this section, differentiation rules, is coming up with shortcuts, really good shortcuts that help us calculate derivatives without having to use the usual formula. The limit as h goes to 0 of f of x plus h, all of that. There are going to be shortcuts that we're going to develop in this section. In my opinion, they are some of the best shortcuts in all of mathematics. So I think you're going to really like them, but we're going to spend some time deriving them. We want to see why they work. We don't want them to just appear out of thin air like a mystery. Okay, so let's go ahead and get started. Okay, differentiation rules. So let's start by reminding ourselves. Recall, given f of x, we can find f prime of x by using f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x. All of that is over h. So I hope that you know that formula by now. We used that formula in the previous lesson in order to answer a bunch of derivative questions. We were able to find f prime for a variety of functions. Some of them were polynomials. Some of them were not. I think we did the square root of x. That's not a polynomial. I think we did 1 over x. That's not a polynomial. So we're seeing that we could do different types of functions. And you might start to wonder, could we find the derivative of other functions like e to the x or sine x? And what applications might that have? And that's kind of where we're headed, is we'd like to be able to differentiate as many functions as possible. But we want to do it with shortcuts. So I'm going to say now we want shortcuts. Because that formula, the definition of the derivative formula, is kind of cumbersome. It's kind of clunky, and it's a big formula with a limit attached to it. And it turns out that there are a lot of types of functions that we can differentiate in a quicker way. But we need to establish these new rules. What I'd like to do is, before we start deriving rules, I want to show you what this is all about. Some of you may have seen this before if you took a calculus class in high school or something. But of course, that's not calculus is not a prerequisite for this class. This class is calculus. So I'm going to assume that you haven't seen this sort of thing yet. And I want to show you what type of shortcut am I talking about. So let's say we're given f of x equals 2x to the 7th plus x cubed minus 5x. Now, this is usually an activity that I like to do in person. Usually, if we were teaching in person, I would write this function on the board, and I would ask, is there someone in the room who has had calculus before in high school or college who can tell me what is f prime of x without showing any work at all? Can you just look at the function and find f prime? Well, since this is a pre-recorded video, I don't have anyone else in the room here to ask. Let's pretend I asked someone, and the student should be able to look at this function, and just from this function and shortcuts that they know, you say 14 x to the 6th plus 3x squared minus 5. That's the derivative. And we're going to learn these sorts of shortcuts. We'll derive most of them, and then a couple of them we might not derive, and we'll just say that they are derived in textbooks. It's a very quick shortcut to go from the problem to the answer without having to do the limit as h goes to 0 of the function and all that. Now, by the way, you could calculate f prime by using the formula we wrote above. You would have this function, 2x to the 7th, plus some other things. And you could imagine putting that into this formula. I guess because this has f of x plus h, and this has x to the 7, well, once you put this into the derivative formula, you'd wind up with a x plus h in parentheses to the 7th. And you'd have to expand all of that. I think we've done that by hand for things like x squared and maybe x cubed. But imagine you have x plus h, all in parentheses, being raised to the 7th, and you have to expand it out, x plus h, x plus h, x plus h, x plus h. And then the next term has x cubed, and then there's, it would be a very big problem to solve that way. Technically, you could do it, but I'm trying to basically explain to you why these shortcuts are so great. They skip all of that. Now, before we just list the shortcuts, let's kind of build them up. We'll start small, and then we'll get there. We'll get there in this video. But I want to say, recall, we can also use the notation d dx. So if I said d dx of 2x to the 7 plus x cubed minus 5x, that d dx notation basically means the derivative of. It's like the derivative of whatever is in here. And we are saying that it is equal to 14x to the 6 plus 3x to the 2 minus 5. All right, so we either use f of x and call the derivative f prime of x, or we can just do this. Say the derivative of this expression or this function equals this. And I think in this section, we're going to use the d dx notation a lot. So that's why I wanted to remind you about it. So let's get started. We're going to have a bunch of different rules, and you could call them properties of derivatives or rules of derivatives. We're going to have at least four rules. So rule 1, the derivative of. I'm going to say the rule first, and then I'm going to prove it. The derivative of just c, where c is a constant, is always going to equal 0 for any constant c. For this, I'm going to show you a proof and an example. I can think of 2 ways we can prove this, probably. I'm saying that if I asked you what's d dx of 8, or what's d dx of 7, or what's d dx of 1,000,000, it always just equals 0 because, well, we're going to see why. So I'm going to prove this to you by using the formula above for the definition of the derivative, where we suppose that the function that we are differentiating, f of x, is just f of x equals c, where c is some constant. So it is a constant function. It should equal limit as h goes to 0, f of x plus h minus f of x, all of that over h, which equals the limit as h goes to 0 of, okay. We should be good with this so far. I want to show that this equals 0, okay? What is f of x plus h in this case? The function is f of x equals c. When I plug in x plus h, what do I get? Well, the function f of x equals c, it's a constant function. It's always going to equal c. No matter what you put in, f of x always equals c. So I get c. Minus, what's f of x? F of x is c. Look at that, we get a 0 up top. C minus c is 0, so this does, in fact, equal 0. And that's a little proof of this rule. I'll show you a little example. Well, there's not really much to say for an example, but how about this? d dx of 4 is 0. Okay? That's an example. d dx of 0 is also 0. d dx of 1 is 0. d dx of negative 1 is 0. In other words, if f of x equals 4, the constant function 4, then f prime of x equals 0. And I'm calling this a shortcut because in the proof I used the formula for the definition of the derivative. But from now on, now that we've established that this is a rule, anytime you need to do this kind of derivative, d dx of 4, d dx of 5, you can just use this rule as a shortcut and just say, hey, I know by rule 1, the answer is 0. It's totally okay to do that. That's kind of that's the whole point of getting these shortcuts established. I also want to show you this as a picture because I've been trying to convey to you that the derivative can be thought of as the slope of the tangent line, so it's also a very visual concept. What does the function, in this example here, this function f of x equals 4, what does this function look like if you were to graph it? Hopefully you know what that picture is going to look like. The function f of x equals 4, or the graph of y equals 4. The y coordinate would be 4, and it would be a horizontal line. Okay, so this is a graph of f of x equals 4. No matter what x value you put in, you always get a y value of 4. So let's say you wanted to know what's the slope of the tangent line to this curve. I mean, it's not really a curve, right? It's a straight line. But anyway, what's the slope of the tangent line to this graph? You could pick any point, like maybe right here. Find what would the tangent line look like. The tangent line needs to follow the same kind of steepness as the black line. So horizontal tangent line. Right there. Horizontal tangent line. What if I looked at a different part of the function? What if I looked over here? Same thing. Horizontal tangent line. No matter what part of this black line I look at, the tangent line will always be horizontal, and 0 is the slope of a horizontal line. So earlier when we started the proof, I said that I think I could think of 2 different ways to prove it. This is kind of another way to prove that this should always equal 0 by thinking about horizontal lines. But anyway, that was enough about rule 1. Rule 1 is just if you have the derivative of a constant. You're probably not going to see that very much as just its own problem. You're probably not going to get asked, what's the derivative of 4? But where we're headed with this is you're going to get bigger problems where maybe part of the problem is just the derivative of a constant. So knowing that that part of the problem is 0 is going to help us. Okay, now I said we were going to have at least 4 rules. So let's move on. Let's get to rule 2. I think they gradually get more interesting as we go on. Rule 2. Oh yeah, actually, this is a really good one. If n is any constant, we would like to have a rule. I'm asking this one kind of as a question first. We would like to have a rule for the derivative of x to the n, because this seems to come up quite often. Now, let's actually do a quick example. For example, let's find one of them. Let's find the derivative of x squared. I know that in our first discussion of the derivative, we used x squared as an example, but I think we were focused in on a specific point when we did that. We were looking at 1, 1. What if we just wanted to find the derivative? I don't think we actually did that. I don't think we found f prime. So real quick, let's do this and see what we get. Limit h goes to 0. I'm not using any shortcuts. We're going to be trying to figure out a shortcut. Let's see, limit h goes to 0. Basically, what I'd like to do is I'd like to try some examples of x to the n and see what answers we get, and then see if we notice a pattern, and maybe from the pattern we could find a general rule. So this is x squared plus 2hx plus h squared minus x squared, all that over h. Actually, it's good practice that we're doing this anyway. Get one of these kinds of derivatives done today from scratch. All right, so we cancel the x squareds. We pull out h, 2x plus h up here. We have h over h. Remember, when h over h cancels, you don't get 0, you get 1. H over h is 1. So I get the limit as h goes to 0 of 2x plus h. I think we had only done that previously with a specific x value plugged in. Now I just left x as a variable. As you do this, h is going to go to the 0. We're going to be left with just 2x. So that's my answer to that. What I'm going to do is I'm going to summarize. I actually think that we've done 3 other examples in a previous video of x to the n. You might not realize it, but this was actually the 4th one that we've done. So I'm going to list 4 that we know. There's the one we just did. We just got 2x. We also, in a previous video, did x cubed. We found the derivative of x cubed by hand, and we got 3x squared. Another one that we did last time was the derivative of x to the negative 1. Do you remember that we did that? Well, we did because we had a problem that asked us to find the derivative of 1 over x. 1 over x is the same as x to the negative 1. So when we found that derivative of 1 over x, we were really finding this answer. And this answer could be written in 2 different ways. We could write it as negative 1 over x squared. I think that's how we wrote the answer last time. I'm also going to write it in one other way. Instead of having the sort of fraction format with x squared on the bottom, we could also call this negative x to the negative 2. And in a minute or two, it's going to become clear why I'm choosing to rewrite it in this form. We also did one more. Do you know that we did the derivative of x to the 1/2? I think when we did this, the problem was not phrased this way. I think that the problem was phrased as find the derivative of the square root of x. But the square root of x is the same as x to the 1/2. And when we did this, we found an answer of 1 over 2 square root of x. Or, I'd like to write this answer in another way also. You know, having a square root in the denominator is not great. And also, just let's try to make all four of these answers kind of look like they fit the same format. 2x, 3x squared, negative x to the negative 2. Let's try to get them all to look like x raised to some power. So this would be 1/2 x to the negative 1/2. Now, that's 4 examples of this type of question. The derivative of x to the n, where n is some constant. We know it when n is 2, when n is 3, when n is negative 1, and when n is 1/2. What these all share in common. Let's look for a pattern, because the pattern is going to help us establish a general rule. What they all share in common is that the derivative of x to the n equals... I'd like you to think about this for a minute. See if you can come up with the general rule. You could pause the video if you need to for a minute. Think about it. What pattern can we get from this? All right, so I know we're not doing this in person. This is just a pre-recorded video, but hopefully you took some time to think about it. I want to point out to you that when we had x squared, the exponent was 2, and a 2 showed up out front. When we had x cubed, the exponent was 3, and a 3 showed up out front. When the exponent was negative 1, there's a negative 1 out front. When the exponent was 1/2, there's a 1/2 out front. So I think when the exponent is n, there's going to be an n out front. It's not just n, there's more to it than just that, but I do think there's going to be an n out front. What comes next is going to be x raised to a power. That's what they all have, right? There's x to something, x to something, x to something, x to something. What power do we have to put here, though? We're going to write something here. Let's look at these 4 examples. When this exponent was 2, this became x to the 1. When this exponent was 3, this became x to the 2. Okay. When this exponent was negative 1, the exponent became negative 2. When the exponent was 1/2, this exponent was negative 1/2. So it seems like whatever the exponent is, the new exponent is 1 less. And we're going to write that as n minus 1. And that is going to be our general rule. That all 4 of these follow this rule. All 4 of these follow this rule, and in fact, this is the general answer. When n is any constant, d dx of x to the n is always going to equal this little formula. So I guess you could say that, you know, it's a shortcut in the sense that it lets us find a derivative without having to use the definition of the derivative. We get to use this formula instead. The idea is that this formula is a lot simpler than the usual derivative formula. There's no limits involved, right? But there's still going to be formulas like this that you need to know, that you need to remember. Now, what I just showed you above is technically not a proof. I didn't really prove that this always works for all constants n. I showed it works for these 4, and then I said, oh, well, based on that, I think this is the pattern. It seems to suggest that this is the formula. I'm going to tell you that in the textbook that I'm referencing, the proof is actually not in this section. The proof comes later because to formally prove this requires some tools that we don't have yet. So we can't really officially prove this yet. We could come back later in the semester and prove this. But for now, we'll say that the pattern seems clear and we can still use this formula. I'd like to show you an example of using this. I'm going to show you 2 examples. First example, if f of x equals x to the 5th, then, according to the formula, f prime of x equals 5x to the 4. Done. That's really nice and quick. You know, and we didn't have to use a limit as h goes to 0. We didn't have to have like something raised to the 5th that has to get expanded, find a bunch of things that cancel out, factor out an h, cancel the h over h, do all of that work. If you did all of that work, this is the answer that you would get. But we get it just by using this formula as a shortcut. I'll show you another one. If f of x equals x to the 1000, then f prime of x equals 1000 x to the 999. Which I guess technically you could do that with the formula from the definition of the derivative. Limit h goes to 0, set it all up. Can you imagine what that would look like? You'd have an x plus h to the 1000 and you'd have to expand it. It would be a nightmare. It would expand just astronomically large. You'd have to look for probably hundreds of terms that cancel out. It would take forever, but this is what you would wind up with. So this is a really excellent shortcut. Okay, so far we have rule 1 is if you have the derivative of a constant. This one right here is if you have the derivative of x to a power. We have what is known as a corollary to rule 2. Now in math, when we call something a corollary, it's supposed to be a fact that follows immediately or almost immediately. Almost immediately. So a fact that's going to follow almost immediately from rule 2 is that d dx of just x equals 1. Because you could apply rule 2 to x to the 1. Rule 2 says that this is true for any n. You know, at the beginning of this page, I'm going to move my paper for just a moment here. At the beginning of this page, I said if n is any constant. So that includes the possibility that n might be 1. How about this? Since I wrote this at the top of the page, if n is any constant, let's also write it here, where n is any constant, just to be, just to have it kind of like attached to this formula. Okay. Okay. So this is x to the 1, so the rule should apply, which says bring the 1 out front. X raised to the exponent is now going to be 1 less. Well, x to the 0 is always 1, so this equals 1. You could also prove this thing using the definition of the derivative, and you would also get 1. That might actually be good practice. Let's try to solve just derivative of x, but putting it into the original derivative formula and find that you do get 1 as an answer. Because I think it simplifies to h over h, which is 1. So that's rule 1 and rule 2, and this is kind of like a bonus for rule 2. So anytime you have to take the derivative of just x, you know that it equals 1. And it's nice in math whenever you get something that simplifies to 1. Rule 3. By the way, let me tell you where we're headed with this. I said we were going to have at least 4 rules. What my plan is right now is I'd like to establish these 4 rules and then spend some time solving problems that combine the 4 rules. That's where they're really going to be powerful, is when you kind of use them, merge them together into one problem. All right, rule 3. The derivative of a constant times f of x equals the constant times the derivative of f of x for any constant c. I'm going to put a big box around this, and then I'll give you a chance to look at it. So this looks good. This is basically saying that if there's a constant in front of something, that you can pull the constant out. Uh, this rule, I kind of want to say that this seems to make sense to me because we know that you can pull a constant out of a parentheses, you can pull a constant out of a limit, you can pull constants out of a lot of things. Turns out that you can pull a constant out of a derivative and have it just be out front. So I'm going to show you a proof of this because, you know, we don't want to just have this class be about memorizing formulas and using them. Anyone can do that. We want you to understand why these rules are true. Be fully justified in using these rules. So let's start with the left-hand side, and we're going to try to show that it equals the right-hand side. What can we do? We could use the definition of the derivative. This would be c times f of x plus h minus c times f of x because of that c out front. Both parts of the numerator have a c, so I think what I want to do is pull the c out, like factor a c out in the numerator. Remember, when I do this kind of thing, I'm writing an equal sign between each expression. This is equal to this is equal to this. They should have equal signs in between them. I'm also writing limit as h goes to 0, limit as h goes to 0. Now, we had a property about limits that said it's okay to pull a constant out of a limit, right? You can't pull a variable out of a limit, and you can't pull out something that's changing. That's really what I should say. H is going to 0, so like you wouldn't be able to pull an h out. But c is just staying as the constant c, so it is okay to pull that out of the limit. You see how nicely this proof works out? Because what we're left with then is c times the definition of the derivative. That is exactly c times f prime of x. And we did it. We proved what we were trying to prove, right? Because we started with the left-hand side of the rule, and we did show that it equals the right-hand side of the rule. Because, you know, this is the same as, this is just different notation, but this is the same as c times d dx of f of x. That means the same thing. We just write it with the prime symbol sometimes. So that means rule 3 is true. And I'll show you an example. Let's say you wanted to know the derivative of 5x cubed. According to rule 3, we can pull the 5 out. We can go further, because according to rule 2, we know what this thing is. We have a 5 out front, and now according to rule 2, this is going to be 3x squared. So this is rule 3, and then this is rule 2. And finally, we should do 5 times 3. 5 times 3 is 15. You get 15x squared as the final answer. So that's what I mean when I said we were going to start combining these rules where you have a problem where you have to use multiple rules. Yeah, it's really good. So what I want to say here is that as you practice these, you'll start to get very fast, and you won't even need to write these middle steps. You know, you might look at this problem, and you might say, I know these rules well enough that I know that the 5 is going to get pulled out. I know that the exponent of 3 is going to get moved out front. The 5 and the 3 are going to get multiplied times each other to give me 15. I know the exponent 3 is going to reduce by 1. So you might be able to, maybe not right now because this is brand new to us, but pretty soon you'll be able to just see this problem and say, I know that that's going to be 15x squared. The 3 times 5 is going to give me 15, and the exponent's going to give me 2. And that's okay to do it. It's okay to do that. It's okay to skip the middle steps for these types of problems. All right, let's look at rule 4. By the way, the reason why I said that we were going to have at least 4 rules, like I was being kind of vague about how many rules there are, it's because we're going to have 4 rules for now. And there are going to be other derivative rules. They're just going to be saved for later. So 4 for now. Although I guess I'm kind of cheating a little bit because rule 4 is kind of like 2 rules in one. So rule 4 says if you have the derivative of a function plus a function, it equals the derivative of the first function plus the derivative of the second function. And I said this was 2 rules in one, and it also works for subtraction. Okay. Makes sense that if this rule exists for addition, that it probably also exists for subtraction. So, I don't know. Do you want to put a box around each of these? Let's go ahead and... Here, we'll put a box around the whole thing, and we'll put a divider in the middle. How about that? That's rule 4. These ones, I actually wasn't planning to spend time proving these right now in this video, but I'll say that you could prove them, I think, using the definition of the derivative, but ultimately where these come from is because we have rules that look like this for limits. We know that a limit, limit of a function plus a function can be split up into a limit plus another limit, and ultimately the derivative is just a limit formula. Right? Limit h goes to 0 of some stuff. So it's a specific limit. Apply the limit rule, and you get this as a derivative rule. I want to say that rules 1 to 4 let us quickly differentiate some functions. I'm saying some functions because, there are still more rules that we need in order to differentiate everything that we want to do in this course. At this point, I want to mention, in particular, 2 of the rules that I am saving for later. 2 of the rules that I'm saving for later are called the product rule and the quotient rule. So if you see those in the textbook as you're looking at, rules 1, 2, 3, 4, if you see the product rule and the quotient rule, I'm saving those to discuss those separately. Okay, so you don't have to worry about them right now. But I claim that even just with these 4 rules, we can quickly differentiate some functions. So let's do one. Example. How about the example that I did earlier where I kind of quickly did this in my head? 2x to the 7 plus x cubed minus 5x. So I'm going to show you the steps. I'm going to break it down into, the different rules that we're using for this one. But the more of these we do, the less I'm going to write. Because the hope is that you get really good at these and get really, really fast at doing these. But for now, this is new to us, so we want to do the derivative of 2x to the 7 plus x to the 3 minus 5x. I said the answer earlier, but now I'm going to show you where it comes from. So, by rule 4, we could split this up. By rule 4, split this up into the derivative of the first piece plus the derivative of the second piece minus the derivative of the third piece. So it's like you have one problem and you split it up into 3 smaller problems. I'm not going to write that, but it is by rule 4, if you're keeping track. Then by rule 3, we can pull constants out, like the 2x to the 7th. You can pull the 2 out of that derivative. So you get this. I'm just going to leave this part alone for now. And then I'm going to pull the 5 out of this. So I guess I used rule 3 on 2 parts of this. First we used rule 4, then we used rule 3. Now I want to use rule 2. Rule 2 tells us how to deal with the derivative of x to the 7, the derivative of x to the 3, the derivative of just x. That was a corollary to rule 2. So we wind up with 2 times 7x to the 6 plus 3x to the 2 minus 5 times 1, right? 5 times 1. You don't even have to write the times 1. That's just going to be 5. And finally, we simplify 2 times 7. And we simplify 5 times 1. And that's the final answer. So we still wrote a bunch of steps, but I hope that you can tell that this is so much faster than using the definition of the derivative. I also want to say that you could write a lot less if you wanted. You could, once you get good at these, you can go straight from the problem to the answer. You can look at the problem and you see 2x to the 7. You say from 2x to the 7, I know the 2 and the 7 are going to wind up getting multiplied by each other to give me 14. I know that x is now going to be raised to the 6 instead of 7. It's 1 less than 7. For the x cubed part, I know that the 3 is going to come down out front, and the new exponent is going to be 1 less than 3, so 2. For minus 5x, I know that the 5 is going to stay because it's a constant, and that the derivative of x is going to get me 1. So that's the whole answer. I'm going to give you one of these to try. I would like you to differentiate. And it's up to you how many steps you show. I mean, I want you to do this yourself, either on paper or in your head. I don't want you to have a calculator do it for you or anything. But why don't you take a minute and you could pause the video and try this, and then we'll talk about it. Okay, so I am going to show some steps because, this is new to us. F prime of x is the derivative of this function. When it says differentiate, it means find the derivative of. So we are looking for f prime. And I would probably split this up into the derivative of the first part plus the derivative of the second part. Next, I'm going to pull out the constants. If you wanted to, you could pull out the constants at the same time that we just did that other step. I knew I was going to split this into 2 pieces. You could pull the -2 out then, if you wanted. Anyway, let's pull it out now and pull out this 1/2 d dx of x squared. And I get -2 times 3x squared plus 1/2 times 2x to the 1. If it's x to the 1, we can just write x. And what remains is that we should simplify this. This is basically the answer. We did differentiate it. We differentiated it, but let's simplify it. -2 times 3 is -6. And 1/2 times 2 just leaves me with 1x. So just minus 6x squared plus x. So can you do that problem completely in your head? Yeah, maybe you can. If you can do that problem completely in your head, that's okay with me. You'd see the 3 and the -2 are going to get you a -6. the 2 and the 1/2 are just going to give you 1 copy of x, and so on. And you'll want to do practice problems like this. I'll be giving you some today, and you should also be working on some outside of this video. But let's talk about something else for this section as well. All right. Note, given a function, oops, let's move the page up. Given a function f of x, its derivative, f prime of x, is also a function. That's not really anything new. We've said that before. But now I'm going to say something new. If f prime of x is also a function of x, then we can do all the things that we like to do with functions. We could graph it, we could talk about its domain and range, we could evaluate it at different values. All of our favorite things to do with functions, you can do to this function, f prime of x. What's one of the other things? What's one of our other new favorite things to do with functions? How about we differentiate it? We can differentiate f prime of x, meaning we are going to find the derivative of the derivative. The result is written like this, and it's pronounced f double prime. F double prime of x. So it looks like f prime prime of x. We say f double prime of x. And is called the second derivative of f. So I think that notation makes sense. We add another little prime symbol. I like that notation. Shows that we did the derivative twice, and we call it the second derivative. I think it's easy to remember that name. It makes sense. We did the derivative twice. It also might seem to imply to you that maybe we could do the derivative again, right? Maybe the result that we get is also a function, so we can differentiate it again. Maybe talk about the third derivative and just keep going and just go crazy doing lots and lots of derivatives. Okay. Here's an example. Suppose we're given f of x equals x cubed minus 5x squared minus x. And I'll do this one for us. We're going to find f prime of x and f double prime of x. F double prime of x. So this is a type of problem that you could see in this section. Besides just the problems that say find the derivative, you could get a problem that says find the second derivative. And now that we've done a couple of these, I'm going to write less. I keep saying that you might be able to solve some of these in your head, so I'm going to do that for this one. Let's find f prime. So we'll just look at each piece. X cubed is going to give me 3x squared. Let's see. Minus 5, and then there's an x squared. So the 2 is going to come down and get multiplied by the minus 5 to give me minus 10. And it's going to be x to the 1 instead of x to the 2. And then minus x is going to give me minus 1 because we said the derivative of x is 1. So that's part of the answer. It wanted us to find f prime. Now we want to find the derivative of that. Can we find the derivative of that? Sure, we'll just do the same kind of stuff, same kind of steps. So look at each piece and find the derivative. So 3x squared. When I take the derivative of 3x squared, the 2 is going to come down out front and get multiplied by the 3 that's already there to give me 6x to the 1. I'm not even going to write an exponent of 1 because I know 6x to the 1 is the same as 6x. Then we have the rest of it, minus 10x. We know the derivative of x is 1. The constant minus 10 is going to stay there. So we're going to have minus 10. Basically minus 10 times 1. But we don't write the times 1. And then this last piece, minus 1. What happens when we take the derivative of minus 1? Well, remember rule 1? Rule 1 says the derivative of a constant is 0. So this is going to basically get us minus 0. I'm not even going to write it because minus 0 doesn't do anything. And that is the second derivative. Now, I need to tell you some notation. When we're given y equals f of x, okay, first, this line that I write here is going to be something we've kind of said already, but I think it bears repeating. The derivative, or we might sometimes refer to it as the first derivative. You know, because if we're going to take the derivative more than once, if we're going to talk about the second derivative and maybe like something like a third derivative or a fourth derivative, we might want to just sometimes call the first one the first derivative, okay? And it can be written in a few different ways. And I think in the previous video, we wrote 6 different ways that you could write it. And for now, I'm just going to focus on 3 of them. You could call it f prime of x, you could call it y prime, or you could call it dy over dx, which we usually pronounce that as dy dx. Those are some of the most common ways that we write the derivative. So now I want to say the second derivative is, well, up above, I said that it could be written as f double prime of x. What's new to us is that I now want to say that it can also be written as y double prime. And what about the dy dx? How would we have to change dy dx in order to talk about the second derivative? Well, this one is a little bit weird, okay? We changed this in a little bit of a weird way. It's going to actually be d squared y over dx squared. Now that might seem strange, but we need to have some 2's to indicate that the derivative is happening twice, and that's where the 2's go. The 2 in the numerator is basically saying we're taking the derivative twice. The 2 in the denominator is basically saying x is the variable both times. Honestly, we might not use that notation very much, but I wanted you to know it anyway. The third derivative, I've been talking about how you might take a derivative a third time. The third derivative is f prime prime prime, and you could call that f triple prime, or y prime prime prime, or d3y over dx to the 3. Believe it or not, these do have real-life applications. Some of that we might see in this course. Some of it shows up in calculus too. Now, here's a question. What if I take the derivative again and again and again and again? What if I want to take the derivative 10 times? Do you think we're going to write f prime, 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 prime? Do you think we're going to write that 10 times? Well, that would get kind of messy. So we have some notation that's going to help us. In general, when we are talking about the nth derivative, where I guess n is a positive integer, okay? Instead of writing the prime symbol over and over and over, what if we wanted to take the derivative 30 times or 100 times? We're not going to just let that go all the way across the page. So we have a different notation that we sometimes use. We write f parentheses n of x. Or y parentheses n, where the parentheses n is kind of up there. It looks like an exponent. I want to emphasize to you that it's technically not an exponent. We're not raising it to the power of n. But I like this notation because it's a nice short way to say that we're taking the derivative n times. And you could use this notation for the third derivative. If you don't want to write the prime symbol 3 times, you could just write parentheses 3. You could use this for the second derivative or even the first derivative if you want. But usually for the first and second and probably the third, we do the prime symbols. And then usually beyond the third one, that's when we start switching over to this notation. Finally, for the final notation here, we need n's, and we don't have to put parentheses around these n's, because these are just like the 2, the 3, then there'd be a 4, a 5, a 6, whatever. An n goes there, so that's fine the way it is. I have something to say about all of these. Not the first derivative, but all the ones beyond the first derivative. We call these higher order derivatives. So if you ever see a book talking about higher order derivatives, it just means the second, third, fourth, and so on, taking the derivative more than once. Here, I'll give you a little problem to try. Given y equals x to the 4th plus 3x squared, I'm going to ask you to find y triple prime. So I'd like you to pause the video, take a minute, and see if you can do that. Okay, so to answer this, one thing is that in order to take the derivative 3 times, we have to find y prime and y double prime first, right? Like we can't just go straight to the third derivative. We have to find the first derivative, second derivative, and then we can find the third, which is what it's ultimately asking for. Let's use these shortcuts that we've established today, and let's try to do it without writing so much. But if you need to write more and break it down into all its little pieces, it's perfectly fine to do that. I see x to the 4, and I say that's going to give me 4x to the 3. I see 3x squared, and I say that's going to give me 6x. That's the first derivative. I'm not going to put a box around that because that's not what the question was asking for. But I needed that so that we can move on to the next part. Next part is the second derivative. So derivative of 4x cubed is 12x squared. Derivative of 6x is 6. We need the next one. By the way, I'm going to hold off on the, you might be tempted to, you might see this and you might be tempted to, factor out a 6. Or factor out, probably factor out a 6. Let's not do that. Let's just leave it like this, because I think it's in a form right now that's kind of easy to differentiate. And I don't know what's going to happen if I change it to some other form. It might get harder to differentiate. Okay, derivative of the first piece, so the 12x squared, the 2 times 12 is going to get me 24. I'm going to get 24x plus the derivative of 6. 6 is a constant, so the derivative of a constant is 0. So there's kind of a plus 0. We don't need to write plus 0. This is the answer. 24x. And that's also a function, and you could keep finding derivatives of that and keep going. All right. So that's the answer to that one. Nice use of the shortcuts that we established today. I want to show you something. We finished answering the problem. Okay, we're completely done. I'm going to say note. What if we keep going? I'm just curious. I'm thinking, what would the next one be? This was the third derivative, so then maybe we write it this way, y parentheses 4, like we're taking the fourth derivative. So the derivative of 24x would be 24. Let's keep going. The derivative of 24, well, 24 is a constant, so when I take the derivative of a constant, I get 0. Okay, let's keep going. Let's take the sixth derivative. Okay. I want to take the derivative of what we just had. What we just had is a 0. 0 is a constant. So when I take the derivative of a constant, I get 0 again. It seems to me like from now on, if I take the 7th, the 8th, the 9th, and so on, if I keep taking derivatives of 0, I'm always going to get 0. Technically, that does keep going, but they're all going to be zeros the rest of the way forever. You might be wondering, does that happen to every function? Like any function? Like is it true that for any function, if you take the derivative enough times, you'll eventually just get to zeros? You could try another function if you're curious. You could actually, like, I'm going to move the page for a moment. You could try that with this one up from earlier. The same thing will happen if you try it on that one. But does it happen for every function? That's actually a good question. I know I was the one asking it, but I'm saying, you know, maybe this occurred to you. Maybe you were wondering this. I'm going to tell you the answer is no. This does not happen necessarily for every function. However, this behavior does happen for every polynomial. Every polynomial, if you take the derivative enough times, you eventually get to just zeros. Okay, but there's more to math than just polynomials, other types of functions that might not do this. But okay, for the sake of discussion though, when we have a polynomial, notice that the problem was a 4th degree polynomial. When we took the derivative, we got a 3rd degree polynomial. We took the derivative of that, it was a 2nd degree. We took derivative of that, it was a 1st degree. Took the derivative of that, and it was a constant function. And then from that point onward, it was all zeros. So it seems like for polynomials, at least, this might not be true for all functions, but for polynomials, it seems like every time you take the derivative, it kind of gets simpler. It becomes a simpler function until eventually it's just zeros. I'll tell you, as kind of this is a little bit of a preview of things to come, but you might be wondering, you know, what's the use of like taking the derivative 7 or 8 times? Like, is there really any use to that? Because the first derivative is the slope of the tangent line, and maybe you could see that there could be some use for that, telling you how, you know, the rate of change of a function. Is the function going upward? Is it going downward? So the first derivative seems like it might have some use. What about the second, third, fourth, fifth? In general, I'll tell you that the more times you take the derivative, the further down the list you go, typically the less useful it becomes. And the 7th, 8th, 9th, 10th derivative are probably not as useful as the first, second, and third. Okay, so in this course, we are mostly going to look at the first and second derivatives. Those are the ones that are the most useful for Calculus 1. Now, if you take Calculus 2, you will use some of the higher derivatives. You will use the third, fourth, fifth, sixth. You'll actually see that there's some use to it. Okay? There is some use to those. For the rest of this video, I'd like to just do a couple more examples. Maybe I'll do some, maybe I'll have you do some. But we're at the point now where I think it would be good just to get some more derivative practice using these shortcuts. How about this? You know what I'm going to do? I'm going to write a few problems, and I'm going to do the first one and then have you do the other ones. So I'll just say differentiate each function. And when it says differentiate each function, if it doesn't specify, like you might say, well, which derivative do we want? Do we want the second derivative? Do you want the first? If it just says differentiate and it doesn't specify, then it means just differentiate once. Just find the first derivative, okay? First function is going to be the cube root of x. I'm going to wind up doing that one for us. Second function is going to be g of x equals 1.2x cubed plus 0.5x. And the third one is going to be h of x equals 3 over x squared. Now, I'll do the first one. I'll do the first one. And we can use the shortcuts from today. We should. We're encouraged to use these shortcuts. I think we could fit these answers right here if we're not going to write too much. Okay, so maybe I don't know, section it off like there's the problem, and here come the solutions. Part A, we do f prime of x equals, so we want the derivative of the cube root of x. Have we talked about any rules today that would cover the cube root of x? Well, yeah, because the cube root of x, you should know that this can be thought of as x to the 1/3. So we want the derivative of x to the 1/3. Just like the square root of x is x to the 1/2, the cube root is x to the 1/3. So this is following that rule. I think we called it rule 2, when you have x raised to the n. So that rule said you pull the exponent out front, 1/3 x, and then you raise it to a new power, and the new power is going to be 1 less than what the exponent started as. So what is 1 less than 1/3? It's going to be minus 2/3. And that's the answer to that one. Okay? So why don't you take a minute, pause the video, and try part B and C. So for part B, these functions are called g and h. That's fine. I guess if the function is called g, then what we're really looking for is g prime. And it's the derivative of 1.2 x cubed plus 0.5x. Okay, so the 3 is going to come down and get multiplied by the 1.2 that's already there. It's going to give me 3.6x squared. And then the 0.5x, I know that the derivative of x is just 1, and the 0.5 stays there to give me 0.5 times 1, which is just 0.5. So like that. And finally, part C, the problem was h of x, so I guess we're looking for h prime of x. Do we know a rule for this one? Like 3 over something? 3 over x squared? What I would like you to see is that, I'll just write it over here. What I'd like you to see is that the derivative of 3 over x squared can also be thought of as the derivative of 3x to the negative 2. So I was hoping that you would notice that. X squared in the denominator is the same as just x to the negative 2. And then once you see that it's that way, you say, oh, I could pull the 3 out. 3 was a constant, so we could pull it out. And now look at that. We have x to the n. N happens to be negative 2, but it's the x to the n rule. So the negative 2 is going to come down out front, get multiplied by the 3 that's already there, give me negative 6. And then we have x raised to the, we need it to be 1 less than negative 2. So negative 3. And you could write the answer this way, or another way you could write the answer for this type of problem, either one is fine. You could write it as negative 6 over x cubed. Either one of those is fine. I'll just give you a chance in case you're writing any of that. Okay, I've got one more that I want you to try for today. So, example. Wait till I write the full problem, because this is going to ask something slightly different. So, given f of x equals 100x cubed plus 20x squared minus 30x plus 4,000. And this problem is going to say, find all x values if there are any such that f double prime of x equals 0. Find all x values such that f double prime of x equals 0. So this is a place where you could pause and give this a try. Okay, so many of the problems in this section have just been, find the derivative, find the derivative, find the derivative, or maybe find the second derivative. So here I thought I would give you one that's it's asking for something slightly different. So let's work on this solution. Well, we need the second derivative. Let's go ahead and just find the first derivative. So we'll go one piece at a time. 100x cubed is going to be 300x squared plus, this is going to get me 40x. This is going to get me minus 30. And the plus 4,000 doesn't even matter because the derivative of a constant is nothing. So that 4,000 doesn't even matter. It didn't even matter whether that was there or not. That's the first derivative. We want to find the second derivative. So let's find the derivative of this. That's going to be 600x plus 40. We want to know x values so that f double prime of x equals 0. So take what we found for f double prime, which was 600x plus 40, and set it equal to 0. And now we're going to solve for x. This little equation. We're going to solve this little equation for x. This says 600x equals negative 40. Let's simplify it a little bit, right? Let's make it maybe like 60x equals negative 4. Just get rid of one of the zeros on each side. All right, so I get x equals negative 4 over 60. Is that the answer? Should I circle that or put a box around that? I hope what you're thinking is we should simplify it further to get full credit. Simplify it to negative 1 over 15. And that is the answer. That is the x value that makes f double prime of x equal to 0. And you could check it. Take this that we said is the answer, put it into f double prime, and verify that it winds up equaling 0. Okay, so this was really just another derivative problem, but it had one extra thing it was asking, and you had to figure that out. Derivative problem, and then a little algebra problem after it. So that was our section on derivative rules. A lot of the problems were just, here's a function, find the derivative of it. I'd like to emphasize right now that there are definitely some functions out there that we do not know how to differentiate yet. So that's going to be coming in the upcoming sections. So don't feel like you know how to differentiate everything right now. I mean, what about trig functions? What about exponential functions? What about like weird combinations of polynomials and trig functions and stuff? So that's where we're headed is, the functions that we're differentiating are going to get more complicated. And we're going to start to see some applications of them. I think in the next section, we're going to see some word problems and some stuff that we can do with derivatives. For now, I would say this was a pretty important section. These shortcuts, we're going to be using them all semester. So I would encourage you to make sure you understand these rules, make sure you do practice problems, work on the homework, ask me questions if you have any questions, and make sure you feel good about these derivative rules because we're going to have more derivative rules later that build on these. Okay? All right, so that's it for differentiation rules. I'll see you next time. Have a good one.